Hello everyone. On this video we will be looking at related rates, sometimes called optimization. Okay, so really optimization is just making the best use of your resources. So that's why sometimes it's called that. But for the most part, most books will call it related rates. Okay, but basically it's just problem solving. Alright, so starting off, what we'll do is we'll kind of set some guidelines, a process that you can follow. Problem solving guidelines. Okay, so your first step is you want to identify all the given quantities and equations. Okay, identify all given quantities and equations. Okay, draw a sketch if it helps. Okay, it doesn't have to be anything award-winning. You just sketch it out so you can visualize exactly what you're looking for. Okay, so 2, you want to write your primary equations. And I'll show you what that looks like in the examples. Write the primary equations for the quantity to be maximized minimized, okay, or even in some cases just or a change to be solved. Okay, so sometimes you're looking for the maximum, sometimes you're looking for the minimum, sometimes you're looking for the rate of change. All right, so our third step, move that up. Okay, only if necessary, sometimes you don't have to do the third step, but only if necessary, you're going to reduce the equations in step 2. Reduce the equation in step 2 to having one independent variable. Okay, now this could involve using a secondary equation. This could involve a secondary equation. Let me clean up that Y a little bit. Here we go. Now 4, if you need to, you find your domain, but for the most part, a lot of the times the domain is pretty obvious. Identify your domain if necessary. Okay, so you just want those values to make sense. Okay, so if you're looking for the length of a building, you're not going to use a negative number. So you know the length of that building would have to be positive. So it's little things like that. You just want it to make sense. Okay, now once you're done with all that, now you should have enough information to determine your minimum, maximum, or rate of change. determine the minimum, maximum values or rates of change using the techniques you've learned so far. Using the techniques you have learned so far. Okay, so for example, if you're going to use the first or the second derivative test, critical points, or etc. Okay, so you're basically just going to use what you've been learning so far. That's really it. All right. So if you are still writing, feel free to press pause, but we are going to go ahead and move on to our first example. All right. Okay, so let's say for our first example, let's say you have the product is 192 and the sum is a minimum. Okay, find two positive numbers that satisfy the requirements. Okay, so this really isn't a story problem. This is just to kind of, I guess, invite you to the uses of the steps that we previously mentioned. Okay. All right. So our first step, we find out what's given. Okay. So we know the product of two numbers is 192. So we'll say x times y equals 192. All right. Now second, what's our primary equation? Okay. So our primary equation is what we're looking for our answer. Okay. So we know the sum is a minimum. Okay, so we have x plus y equals, we'll put some value s. Okay, now third, remember that optional third step? Where you want one independent variable. Okay, now here you have x and y. You have x and y. You don't want a variable of just x and y. Okay, so we have s equals x plus y. But what we're going to do up here is we're going to divide both sides by x. So we have y equals 192 over x. Okay, so now we can replace y with 192 over x. So we have s equals x plus 192 over x. So that leaves us with two independent variables to just having one independent variable. So s is just a function of x. So x is our only independent variable. Okay, so that's how that third step would look when you're just changing it from 2 independent variables to 1. Okay. Now your domain, I think it's safe to say, since we're looking for 2 positive numbers, your domain is just x is positive and y is positive. Again, you don't have to do this step. It's sometimes just helpful to look at it so you know not to forget that they're both positive. Okay, so your 5th step, okay, we're going to find the rate of change to find our minimum. Okay, so in order for that sum to be the minimum, we have to find that minimum value. So we're basically using the rate of change to find where that minimum exists. Okay, so since this is our function, we want to find the rate of change of s with respect to x. So the derivative of x is just 1 minus, we'll work that out over here, the derivative of 192 over x. We're just going to make that 192 times x to the negative 1 power. Okay, so if we take the derivative of that, that's just 192 times negative 1 times x. We subtract 1 from there, which makes it x to the negative 2 power. Okay, so this is just negative 192 over x squared. All right, so in order to find our minimum, we have to find our critical point. And our critical point is where the first derivative equals 0. Okay, so in other words, we have to find where 1 minus 192 over x squared equals 0. Okay, so if we just add that to both sides, we have 1 equals 192 over x squared. Multiply both sides by x squared. That's just x squared equals 192. We square root both sides. Then x is equal to positive or negative square root of 192. But since we're only dealing with positive numbers from our initial problem, we know we don't need the negative. Okay, now we know that since y is equal to 192 over x, oh, sorry about that, we just replace x with square root of 192. So y is equal to 192, we just make that square root of 192 times square root of 192 all over x, which is square root of 192. So that means y is also square root of 192. Okay, so the smallest sum that you can have that their product will equal 192 is square root of 192 plus square root of 192, and then multiply square root of 192 times square root of 192. So we know that S is a minimum sum when both x and y equal square root of 192. So we have our y value there. All right, so that was kind of just an introduction to the steps. Okay, so if you are still writing, feel free to press pause, but we're going to go ahead and move on to our next example. Uh-oh, you kind of straighten up the papers here. There we go. Alright, so let's say, for example, we know the perimeter of a rectangle is 100 meters. You want to find the maximum area. Alright, so just like before, our first step, we're going to see what's given to us. Okay, so we know the perimeter is 100 meters. So if we draw out our rectangle, and you have x and y, we know the perimeter equals 100. Which is just basically adding all the sides together. So we have x plus x. So the perimeter equals 2x plus 2y. Or you can just make it 2x plus 2y equals 100. Okay, so that's given to us. We can kind of figure that out just by the information given. Okay, now second, we need our primary equations. Okay, so we're looking for the maximum area. Okay, we know that the area equals length times width, or x times y. Alright, now our third step is we need to reduce this to one independent variable. You can't have it a function of x and y. Okay, so how do you do that? Well, you use what's given to you. You notice you have that here. So 2x plus 2y equals 100. So if we subtract 2x from both sides, you have 2y equals 100 minus 2x. And if we divide each one of those by 2, we have y equals 50 minus x. Okay, so that means we can get our primary equation, a equals x times y, and we can replace that y with 50 minus x. So that's a equals x times 50 minus x. So if we go ahead and distribute that x, we have our area is equal to 50x minus x squared. Okay, so we have our primary equation, but we have it with just one independent variable. Okay, so that helps us a lot. Okay, so it's no longer a function of x and y, it's just a function with just an x variable, that one independent. Alright, so the fourth step, and again, if you wanted to, you could skip the fourth step, just identifying your domain. We know x and y has to be positive. Alright, so your fifth step, you want to find your maximum area. That's what they're asking for. Okay, so derivative of the area with respect to x. Okay, so the derivative of 50x is just 50, minus the derivative of x squared is just 2x. Okay, so to find the maximum, remember we have to find the critical point first. Which is just when that first derivative equals 0. So that means you're just going to make this equal 0. So 50 minus 2x equals 0. So if we add 2x to both sides and divide by 2, we end up with x is equal to 25, which is our critical point. All right. So, move that up. Now, when x is equal to 25, that means y equals 50 minus x now becomes y equals 50 minus 25. So that means y is equal to 25. Okay, so if you make x equals 25 and y equals 25, that will give you the maximum area if your perimeter is 100. Okay, so x equals 25, y equals 25 will provide the maximum area. All right, now just if you wanted to, just a quick note, you could verify the maximum area. Okay, just given the second derivative of a with respect to x. So if we find the second derivative, that's going to equal -2. Okay, so since this is negative, we know that that's the local maximum. If it was positive, that would have been the local minimum, but it is negative, so that's your local maximum. Okay, just a little additional note there to kind of help you refresh a little bit of some of the information that we've gone over. All right, so if you are still writing, feel free to press pause, but we're going to go ahead and move on to our next example. All right, so let's say you have a farmer plans to fence a rectangular pasture adjacent to a river. Okay, so the pasture must contain 180,000 square meters in order to have enough grass to feed the herd. Well, I'm saying instead of in order to say to have enough grass to feed the herd. To have enough grass to feed the herd. What dimensions would require the least amount of fencing? Would require the least amount of fencing if no fence is needed along the river. If no fence is needed along the river. Okay, so what I'm going to do is I'm going to start you off, but then I want you to give it a try on your own. Okay, so to start you off, I'm going to give you your given. So first thing we're going to do is we're going to draw what we need. Okay, so we have a rectangular pasture, but you have a river here. Okay, now your area is just everything in here. So the area has to equal 180,000 square meters. So you have y, and let's say that'll be your x. Alright, so that will start you off. Pretty much if you use the same method from the previous example, you should be okay. Alright, so I want you to go ahead and press pause and try this one on your own. Alright, so I'm assuming you've pressed pause and you worked this one out. So let's go ahead and verify your answer. Alright, so what did they give us? We know that the area must be 180,000 square feet. Okay, so the area, we know that's the length times the width. Oh, man, it should be straight. There we go. We know that x times y has to be 180,000 square feet. All right, so we have to go to our second step where we'll let S represent the length of fencing material that we'll need. Represent the length of fencing material needed. All right. So in order to get enough fencing for that boundary, we'll let S equals x plus 2y. Okay, because remember, we don't need any along the river. So again, that gives us our primary equation. So we go to our third step and we find our independent variable, because now you're looking, you still have your x and your y as your independent variables. We only need one. Okay, so your third step, your independent variable. Okay, so that means S equals x plus 2y. You notice here, if you divide both sides by x, you have y equals 180,000 divided by x. So we can just replace our y with that. So S equals x plus 2 times 180,000 divided by x. Okay, so that means our S now equals x plus 360,000 divided by x. Okay, so our fourth step, again, if you want to skip the fourth step, you can. But the fourth step is just your domain, and of course, we see that they both have to be positive. X greater than 0 and y greater than 0. Okay, so for your fifth step, of course, we find our minimum value, our minimum material needed. Minimum material. Okay, so we have to find our critical point for this one, which is our first derivative. So our first derivative of S with respect to x is equal to 1 minus, find the derivative of S, or basically using this one. That's why I draw a little square so I don't miss out on which one I'm using. Derivative of x is just 1, and derivative of 360,000 over x is actually 360,000 over x squared. that means we have to find our critical point. We have to find where that derivative is equal to 0. And we move up, running out of room, but we should be able to finish this up here. Okay, so to find where this is equal to 0, we have to find where 1 minus 360,000 over x squared is equal to 0. So if we add that to both sides, we have 360,000. Well, actually, we put the 1 on the left. 1 equals 360,000 over x squared. Multiply both sides by x squared. If x squared equals 360,000, square root both sides, x equals 600. All right. So now we know what our x has to be. We have to find our y. Okay, so we know s. Oh, where is it? Ah, y is equal to 180,000 over x. That's the one I was looking for. Okay, so y is equal to 180,000 over x, which is just 180,000 over 600. Okay, so y is equal to 300 liters. Okay, so those are the lengths of fencing material we'd have to get, or the minimum length of fencing material we'd have to get if our area is to be 180,000. Okay, so if the total length of the fencing material needed is x plus 2y, let me straighten that out, then that means it will be 600 plus 2 times 300, or 600 plus 600, so you have 1,200 total meters of fencing material. That you would need. Alright. So if you are still writing, feel free to press pause. But we're going to go ahead and move on to our next example. Here we go. All right, so for this example, let's say if you have a car company that charges its customers P number of dollars per day to rent a car. Where P could be anywhere from $45 to $200 a day. Okay, so let's say somewhere along the line it was figured out that the number of cars rented per day can be modeled using the linear function N of P is equal to 800 minus 4P. Okay, so what we want to know is how much should each customer or how much should the company charge each customer, per day to maximize revenue. Clean up that E a little bit. There we go. Okay, because if you charge too little, you lose money. If you charge too much, you send them to the competition. Okay, so how much should they charge per day to get the maximum revenue? All right, so let's go ahead and start on this one using our steps. So first step, our given, we know that N of P equals 800 minus 4P is our number of cars rented per day. Okay, so that's given to us. All right, so our second step is our primary equation. Okay, and we need to know our revenue. How much money we're making. Okay, so our revenue would be the number of cars rented. Oh, not minus, times the price of the car. I should probably bring that up a little bit. Times the price of the car. Okay. So if we want to get that into a nice, neat little equation, we'll just make that R equals the number of cars rented times the price. Okay. Now it's not profit, so we're not counting, costs and maintenance and insurance. We're just looking at strictly revenue, how much money's coming in. Okay, so we have our independent variable, but of course, just like before, you have two independent variables. We don't need two independent variables. We just need one. All right, so we need our independent variable, just one. Okay, so we know that our revenue is the number of cars times the price. And we also know that N is equal to 800 minus 4P. So we'll replace this in there. Okay, so that's your revenue is equal to 800 minus 4P times P. So if we go ahead and distribute that, we know our revenue is equal to, we'll just switch that around to negative 4P squared plus 800P. Okay, so this is our primary equation with just one independent variable. Okay, so now our fourth step is our domain. Now this one is a little different than the previous ones because it's between 45 and 200. Okay, so now we determine our minimum and maximum values. Well, our maximum value. Okay, so using our primary equation, our rate of change of our revenue with respect to the price is equal to, take the derivative of that, you have negative 8P plus the derivative of that, which is just 800. Okay, so of course we have to find where that is equal to 0 because that's our critical point. Okay, so that means we have to find where negative 8p plus 800 equals 0. So if we subtract 800 and divide both sides by negative 8, we end up with the price is equal to 100. Okay, now what we can do is we can test that to see if it is the actual price needed to maximize revenue. So we're going to go ahead and test it. Since that's your critical point, we're going to test both the endpoints and that critical point there. Okay, so we have R of 100, which is that value, R 45, and R of 200. To see the max revenue. Okay, because you may think, oh, if you just charge 200 bucks each, you'll make more money. Not necessarily. Okay, so first, R of 100, so we go ahead and plug in R 100 in either one of those. I'll just plug it in there. So you have 800 minus 4 times 100 times 100. Okay, so that's 40,000. All right. So let's try our 45. Okay, if you charge $45 each, that's going to be 800 minus 4 times 45 times 45. Okay, so that is going to be 27,900. Okay, now let's try if you charge $200 each. Okay, so that's going to be 800 minus 4 times 200. Run out of room times 200. There we go. Barely got it. Okay, so if you plug all that in, you actually end up with 0. You break even. Okay, so charging the absolute maximum amount isn't always the best solution. You can see here that you make more money when you charge $100 to rent the car. All right. So if you are still writing, feel free to press pause, but we're going to go ahead and move on to our last example. All right, so let's say for this example, you have a 13-foot tall ladder, and it's leaning against the side of a building. Okay, so let's say if the bottom of the ladder slides away from the wall at a rate of 2 feet per second. Slides away from the wall at a rate of 2 feet per second. How fast is the top of the ladder sliding down the wall. When the ladder is when the bottom of the ladder is 5 feet from the wall. Bottom of the ladder is 5 feet from the wall. All right. So this one, we're going to do the same steps. So first, we look at what's given to us. And this is where it's usually easiest to draw a picture to help you visualize. Okay, so let's say you have the side of a building here. I'm not going to draw the whole building. We're just going to draw this one wall. Okay, and you have a ladder right here. Okay, and you have the distance from the bottom of that ladder to that wall. Okay, so what we'll do is we'll let, since we know that's unless you have a crooked building, that's going to be a right angle, we'll let y equals the height of the wall we'll let x equal the distance from the bottom of the ladder to the wall. Okay, so that's our x there. And we already know that the ladder is 13 feet. So that is going to be 13. So you have the ladder leaning against the building, and that's the distance of the bottom of the ladder to the wall. Okay. Now what this tells us when it says that the bottom of the ladder slides away from the wall at a rate of 2 feet per second, that means this part is sliding back. That ladder is literally just sliding down the wall. So that means the bottom is going that direction, and the rate of change of x with respect to time is equal to 2. Okay, so that means that that x is getting, as that ladder slides down, that x is getting further, is getting bigger and bigger and bigger, because now that part is sliding out. Okay, so the rate of change is equal to 2. Okay, so we need our primary equations. Okay, now what are we looking for? We're actually looking for the rate of change of the height of the ladder as it's sliding out. So how fast is this sliding down the wall when this is sliding out at 2 feet per second? Okay, so our primary equation, since this is a right triangle, our primary equation is going to be x squared plus y squared equals z squared. Or, in other words, since we know that our hypotenuse is 13, x squared plus y squared equals 13 squared. Alright, now this one's a little bit different because it's involving rates of change. Okay, so it's not like you can just, solve this for y and then find your x. You can't do that because you don't know what y is. You don't know what x is. You just know that it's changing. It's not just one value. Okay. Now we know at one point it's going to be this, but we don't know what our rate of change is going, how that affects our value. So we can't just plug in X and say, okay, we're all done. Okay, we have to actually find out, okay, when our rate of change is 2, how exactly does that affect our final answer? Okay, so since we are looking for the rate of change, we're going to use implicit differentiation. Use implicit use implicit differentiation. All right. So actually we can skip steps 3, okay, because we're not just solving for one independent variable. We're going to use implicit differentiation, so we're going to use both. Okay, and our domain is x greater than 0 and y greater than 0. It doesn't have to get more complicated than that. Okay, we know both of those have to be positive numbers. All right. So we're kind of running out of room here. So what I'll do is I'll finish this up on the next page. So if you're still writing, feel free to press pause. But we're going to go ahead and finish this up on the next page. Okay, so that's what we have. Well, might as well mark it as our 5th step. X squared plus y squared equals 13 squared. Okay, so we know that x and y are functions of time. Okay, the rate of change, that remember from our previous page, let me move this over real quick. This is changing as feet per second, so it's a rate of time. So x and y are functions of time that we would just call t. So we take the derivative of each of these using implicit differentiation as functions of time. Okay, so derivative of x squared with respect to time plus the derivative with respect to time of y squared plus the equals the derivative with respect to time of 13 squared. Move that up. There we go. Okay, so the derivative of x squared with respect to t, if you remember your implicit differentiation, you take the derivative of the whole thing, so that's 2x, and the derivative of what's inside, times dx dt. Plus, take same thing with y, take the derivative of the whole thing, so you have 2y times derivative of y with respect to t. And that equals the derivative of a constant is just going to be 0. Okay, so if you remember from the previous page, we're solving for this one, our dy dt. Okay, so that means if we subtract 2x dx dt, okay, so you have 2y times dy dt equals negative 2x dx dt. Then divide both sides by 2y. You have your dy dt equals, you have negative 2x over positive 2y. That simplifies to be negative x over y times dx dt. Alright, so now we have everything we need to solve this. Okay, we know that rate of change with respect to x, well, rate of change of x with respect to t is 2, and we know that x is equal to 5. Well, I thought we had everything we needed for it, but we don't because we still don't know what y is. Okay, so we still have to solve for y. As you can see, I make mistakes too, but as long as you catch them in time, you're good. Okay, so how do we solve for y? There we go, right up there. Okay, so we know that x squared plus y squared equals 13 squared. And we know that x is equal to 5. So if we subtract x squared from both sides, we have y squared equals 13 squared. And instead of x minus x squared, I'll put minus 5 squared. Okay, so y squared equals 144, because it's 169 minus 25. Okay, so y is equal to positive or negative 12. Okay, we know our domain has to be greater than 0, so that means that y is equal to 12. Alright, so that was pretty painless. So, going back to our formula, derivative of y with respect to t, remember that's negative x over y, I'll just go ahead and put that down again, times dx dt, that's going to equal negative x equals 5, y equals 12, so negative 5 over 12, bring that up some, times our rate of change of x with respect to t is 2. Okay, so that's going to equal negative 10 over 12, which simplifies to equal negative 5 over 6 feet per second. Okay, so that's how fast the top of the ladder is sliding down the side of the building. Okay, when we know that the bottom is sliding out at 2 feet per second. All right. So hopefully this video made sense, and I will see you on the next video.